Okay, so today we are going to introduce the fundamental group, and then in the next lecture we are going to see the relation between the fundamental group and the simply connected covers of a space. So today's lecture is going to be somewhat short. And then terminology. So we assume X to be a topological space, yeah, and then inside a topological space take 2 points. And then a curve from one point to the other. Well, it should be, we define it to be a continuous function, yeah, from the unit interval to X that somehow starts in one point and ends in the other. A curve that connects a point to itself is also called a loop based at such point. And then the basic operation or a basic operation that one can define on curves is that if I have two curves and somehow they can be concatenable, so if I have two curves, one of them ending at a point and the other one beginning precisely at that same point, in that case we can define the concatenation, which I'm going to denote by this sigma, this funny dot tau, and observe that I'm going first from x0 to x1 via sigma, and then from x1 to x2 via tau, and somehow the concatenation, for the notation for the concatenation is opposite to the notation that we are used to when composing functions. So that's important to always remember. And the concatenation, well, what should it be? I mean, the point is that because I'm defining a curve to be given, always in terms of the unit interval, somehow, that i.e. somehow I'm allowing as domain of a curve only the unit interval and excluding arbitrary intervals of the form a comma b. Because of that, to define the concatenation, you see, I cannot just say, okay, so take the interval 0, 1 and then 1, 2, right? So take the interval 0, 2 and then define the concatenation there. But I have to work with the unit interval. Okay, but the idea is that if I have the unit interval, I cut it in half, precisely at 1/2, and then somehow with the first half interval I parameterize sigma, and with the second half of the interval I parameterize tau, right? But then just realize that then this, let's say the first half, somehow I have first to enlarge it to the whole unit interval, so that here I can apply sigma. And so in the first half, in the interval 0, 1/2, then I have to traverse sigma, but twice as fast. And similarly, for the second half of the interval, then what I realize is first I double it up, but of course I multiply the whole interval by 2. But then I realize that when I do that, I end up with the interval 1, 2, and so from the interval 1, 2, I still have to subtract 1, so that I end up really in the interval 0, 1, in which I can apply tau. Right? So in the interval 1/2 1, I apply this this formula tau of 2t minus 1. With the and again the basic idea is that with this one I go, in the first half I go with sigma, and in the second half I go with tau, and then of course I would have to check continuity, but you see I'm defining a function on piecewisely on two closed subsets of my whole interval. And sigma and tau coincide in the intersection of the two closed subsets. Not sigma and tau, but rather these two formulas, they really coincide in the points of intersection of the two pieces of definition, and that guarantees that this formula really produces a continuous function from the whole interval to x. Okay, so that's the concatenation. If you think about it, I'm really doing the obvious thing. And this is the basic operation from which the fundamental group of x arises. Now, the fundamental group is going to be a group, so there's going to be inverses, and then the inverses are really going to arise from the construction here. So if you give me a curve in x, we define this sigma minus, again from the unit interval to x, by traversing sigma but in the opposite direction, right? So so if sigma does something like this, then sigma inverse really goes in the opposite direction. It traverses, it has the same trace in the same image, but it goes in the opposite direction. And finally, the notion of homotopy between curves. Which is a specific situation of a more general notion of homotopy between continuous maps. But anyway, for two curves, so two continuous maps from the unit interval to x, somehow the notion of homotopy from one to the other relative to the endpoints, what I want to capture with the definition is somehow this picture, which is that you see I have my two curves, and somehow first of all I assume that they are curves from x0 to x1, and I want the notion of homotopy to capture the idea of that sigma naught be deformable to continuously deformable to sigma 1, and that in each step of the deformation one has a curve again from x0 to x1. So given my two curves from x0 to x1, I'm at a homotopy from sigma 0 to sigma 1 relative to endpoints. So that relative to endpoints makes reference to wanting all the intermediate curves to go from x0 to x1. Is a continuous function from the unit interval cross the unit interval to x, such that, and here what I'm going to think of the first component as if it were time, And then the second component, I'm going to think of it as the parameter for my curves, as here. And so in the first condition, thinking in those terms, thinking that the first coordinate is time, says that at every time, at every point in time, what I have, what h with h at that time is a curve from x0 to x1. So at each point in time of the deformation, I have a curve from x0 to x1, and it is this from x0 to x1 that this makes reference to relative to endpoints, because I'm asking that each of these intermediate curves has the same endpoints as sigma naught and sigma 1, and of course that the deformation starts with sigma naught and ends with sigma 1. And here is the picture. So since I'm thinking of the first coordinate as being time, somehow I'm thinking of the vertical coordinate of the verticals as being the parameters of the curves, of the intermediate curves. So so this would be mapped to sigma naught, this to sigma 1, and then in each intermediate vertical segment would be a curve from x0 to x1, and then I think of the deformation of the deformation being parameterized here horizontally. So somehow the image of that would look like this. Okay, and then relative to endpoints is that all of this segment in the boundary of the unit square goes to x1. And all of this segment in the boundary of the square goes to x0. Notation for when for when there exists a homotopy from one to the other. And then some exercises. Here I'm signaling the handing exercises for next week. And so something useful in when thinking about whether in many situations about whether between given curves there exists a homotopy or not is drawing this sort of diagrams to as mnemotechnics of what is happening in the actual space X. So let me illustrate this with some of this. So first, homotopy relative to endpoints is an equivalence relation on the set of all curves that go from one point to another. Right. So here I'm fixing my topological space X and my 2 points x0 and x1, and I'm considering the set of all curves that go from one to the other. And homotopy relative to endpoints is an equivalence relation there. And somehow the mnemotechnics would be like this one. So for the for transitivity, let's say. So let's say that what I have is let's say here a curve. Oops, this is a curve sigma naught homotopic to a curve sigma 1 from x0 to x1. So this I indicate, let's say here, x1 and x0. And let's say that I also have a homotopy relative to endpoints between sigma 1 and, let's say, sigma 2. And then of course what comes to my mind, if I have this situation, and then here let me also indicate x1 and x0 and x0. Yes. What comes to my mind, of course, is I have this square, and the image of this is equal to the image of this, and so somehow what comes to my mind is to just put the two squares together, right, and then define some continuous function from the rectangle 0, 2 times 1. But then I remember that somehow I'm really in the formal definition. I'm not allowed to do that. I have to define things just from the unit square. So I proceed in a similar manner to how I proceeded here, and that is illustrated in this diagram. So the homotopy from sigma naught to sigma 2, so transitivity. What can I do? Well, I can I take the rectangle 0, 1/2 times 0, 1, and then and that one first I enhance it, I enlarge it, and then go with my first homotopy from sigma naught to sigma 1, and then consider the second rectangle 1/2, 1 times 0, 1, and that one enlarge it and then go with the homotopy I have here. And in the end, what I should be getting is since I'm defining here a function in piecewisely, right? I'm defining it by defining its restrictions to these to closed subsets, and since I am on the intersection, these two actually coincide. That's how I know I should be getting really a continuous function on the whole square, and I know that, you see, all of this goes to x0, and all of this goes to x0, and all of this goes to x1, and all of this goes to x1. So again, I obtain a homotopy from sigma naught to sigma 2 relative to endpoints. And kind of just to illustrate that this is more than just the picture, that one can really read everything from this sort of schematics, from this type of diagrams. So let's see, what should be the actual rule. So sigma naught of S T should be, so remember that, not sigma naught, I'm sorry, H of ST, and then remember that the first coordinate is time, the time through which I'm deforming the curves, and so I have two situations, and it's before time 1/2 and after time 1/2. So it's here it should be if S is in 0, 1/2, and if S is in 1/2, 1, and in here, well, I have to multiply S by 2 and go with the homotopy I already have. So it would be like my H1 from 2S of 2S comma T, and in the second one I have to enlarge this one to 2, but somehow I have to multiply by 2, but then I end up with in 1 2, so I have to subtract 1, so it would be h2 2s minus 1 comma t. And here, of course, where h1 and h2 are my homotopies given a priori, because I wanted to prove transitivity. So somehow I assumed sigma naught homotopic relative to endpoints to sigma 1. So I assume h1 given, and I assume that sigma 1 relative to endpoints, homotopy relative to endpoints to sigma 2. That is, I assume h2 given. And you see, and this is, and then you see, I could read what the formula should be just from this diagram. And in turn, somehow this diagram, I really could read it just from saying, okay, so the obvious thing to do is to just put one square next to kind of just juxtapose the squares, and then just realizing, okay, but then in order to obtain what is really something that is really allowed, then I just shrink that picture to this picture. Okay, so let's do one more. So yeah, okay. So sorry. This is transitivity, and something very easy to check is that every curve is homotopic relative to endpoints to itself, and that if sigma naught is homotopic relative to endpoints to sigma 1, then the converse is also true. So sigma 1 is homotopic relative to endpoints to sigma naught. I mean, it's just traverse. That would be traverse the homotopy, but in the opposite direction, right? So it would be like the new h would be the old h of 1 minus s comma t. Okay, so let's now move to the second one, which says that homotopy relative to endpoints is compatible with concatenation, right? Provided concatenation makes sense. So if sigma naught is homotopic relative to endpoints to sigma 1, so if sigma naught can be deformed to sigma 1, right, and of course both of them going from, see, this already says that both sigma naught and sigma 1 have the same endpoints, and tau naught and tau 1 are homotopic relative to endpoints, and moreover, these two end precisely where these two begin. In other words, I have, not only do I have these homotopy relations here, but also the concatenations, concatenating this one with this one and this one with this one makes sense. Then the concatenations are homotopy relative to endpoints. That is, homotopy relative to endpoints and concatenation are compatible, provided concatenation is makes sense. And here, this is the diagram that helps me, because you see somehow here what I have is, I'm assuming that somehow I have here sigma naught, sorry, no, it's not there, it's here. Sigma naught homotopic to sigma 1 relative to endpoints. So let's say x naught, x1. And I also have tau naught homotopic to tau 1 relative to endpoints. And moreover, where the sigmas end is where the taus begin. So here I can put x1, and let's say here x2. And moreover, I want to concatenate, right? So first traverse sigma naught and then tau naught, and first traverse sigma 1 and then tau 1. So first sigma naught and then tau naught, and on the other hand sigma 1 and then tau 1. And so what comes to my mind is to put this square on top of the other square here, and then just say okay, and then since you have this homotopy to x, and this homotopy to x, then just put the one square on top of the other, and then define a homotopy from this rectangle. So that's the what comes to my mind. But then I remember that everything has to be defined in terms of just the unit square. So what I do is just shrink the height, yeah, and then the diagram then becomes this one, right? So on this lower half, then first I enlarge the height and go with the homotopy I already have from sigma naught to sigma 1, and then on the top half again enlarge, and then go with the homotopy I have for the second one. And here again I can with this diagram I can also cook up the formula, so or a formula. So let me do it. So let's say that here again I have I'm assuming this, so I'm assuming that there's a homotopy H1, and here I'm assuming that there's a homotopy H2, and then my H from my H would be, sorry, my H of S comma T. Recall that the first coordinate is the time during which I deform. And here now, of course, the consideration is the height, right? So it's if T is in 0, 1/2, and here if T is in 1/2, 1, and then here is 8. With this one I have to multiply height by 2, right? And then the S is okay. So HS 2T. And in this one, I multiply by 2 and subtract 1, so that I really end up in the so that the result really ends up in the interval 0, 1. So H2 S comma 2T minus 1. And the way to justify that it's continuous, it's because you see, I'm defining a function again piecewisely by telling you its behavior in these two closed subsets, and in the intersection of these two closed subsets, the two rules, the two pieces, give me the same. They give me x1. Okay, then 3. And for 3, the handling exercise is to explicitly write down a formula for this. So what this says is if sigma naught is homotopic relative to endpoints to sigma 1, let's say through some homotopy H, then traversing sigma naught in the opposite direction is homotopic relative to endpoints to traversing sigma 1 in the direction opposite to that of sigma 1. through some homotopy, and the exercise is to give is that you give me the explicit formula of that homotopy. For 4 is something similar, and so you see here in 4 what I'm really saying is, if I have curves that if I have 3 curves, sigma, tau, and rho. So in particular, each of them is I'm assuming it to be a continuous function from the unit interval to x. And if tau naught begins where tau begins where sigma ends, and rho begins where tau ends, so that I can concatenate sigma and then tau, and tau and then rho, and actually I can form these concatenations, sigma, and then concatenate it with, and then traversing the concatenation tau dot rho, or the other way around, right? Kind of to test associativity. So I have the 2 different ways to associate, and these 2 curves, they are not the same. Not in general. They are almost never the same, I would say. But they are homotopic relative to endpoints. And the exercise here is to give an explicit homotopy relative to endpoints between the 2 curves, between this curve and this curve. And the diagram, or the diagrammatics would be, can be just drawn here, something very simple, where here I'm writing the point. This is 1/2. This is 1/4. This would be 3/4. And here it would be again 1/2. And you see somehow here, so this one, the parametrization of this one is visualized here like this. So because this is a concatenation of 2 things, sigma. Oops, I made a mistake. It's the other way around. Sorry. This one is really here. Yes, sorry, I messed up the picture. Sorry, here, because here this is the concatenation of 2 things, namely this one and rho, and this one in turn is a concatenation, and so rho should be parameterized here, and sigma dot tau here. But then this one is split in, you have to split the corresponding interval in half. So this is what ends up parametrizing sigma. This is what ends up parametrizing tau. And this is what ends up parametrizing rho. So let me just write it schematically as sigma, tau, and rho. And on the other hand, here, this one is the concatenation of 2 things, namely sigma and this thing. And this thing is in turn the concatenation of 2 things, namely tau and rho. And so here one wants this to parameterize sigma, one wants this to parameterize tau, and one wants this to parameterize rho. And also somehow through the deformation, you see one wants, for instance, this parameterization to start somehow kind of enlarging. This one somehow one wants to just kind of maintain it, but then maintain it in size. And this parameterization one wants to somehow shrink it. And then I almost solved the exercise. So now with this diagram, what I want you is to provide an explicit formula, right, of like h of 0, 1 times 0, 1 to x, and then h of st equal to what? Similar for 5. In 5, what I'm saying, so here I'm denoting the constant curve at certain point, right? I mean, somehow as a function is the constant function from the interval 0, 1 to x, and the constant value is the subindex. So what I'm saying is, if I consider the constant curve at sigma naught, and I concatenate it with sigma, the concatenation really makes sense. So you see here, if for this concatenation, the first half of the first half of the time, I am just like parked at sigma naught, and then starting at time 1/2, I start traversing sigma, and I traverse it twice as fast as I used to traverse sigma. That's what this is telling me, and that is homotopic relative to endpoints to just traversing sigma, and is homotopic relative to endpoints to traversing sigma twice as fast first, and then parking, staying still for the last half of the time in sigma 1. And so again, here I want you to give me the two an explicit formula for this homotopy relative to endpoints, and an explicit formula for this homotopy relative to endpoints. And for instance, for this one, the diagram is here. So I want to start here with this C sigma naught, and here sigma, and I want to end up only with sigma, right? So, and the idea somehow is then, I mean, so here so you see here in at the beginning, all this first half I remain parked at sigma of 0 at the starting point of sigma, and then I traverse with sigma. And so somehow the idea is that the idea in this diagram is that the homotopy that again here I want you to tell me h of s tau equal to what. The idea here is that then the time you remain parked at the starting point of sigma becomes every time each time smaller. So somehow this becomes like a kind of some sort of dead area in a way. And all of this is the handling exercise for next week. So let me write it here. So and finally, concatenating sigma with sigma minus, it really is homotopic relative to endpoints to just not moving, right? And then kind of if I start first with sigma and then going back, then it should be not moving but staying at the starting point of sigma. And if I do it the other way around, so if I have sigma here, if I first go with sigma minus and then with sigma, then of course it has to be not moving but staying, but at the end point of sigma. Okay, and here is the diagram. And so yeah, a good exercise is then to first fill in this diagram, you know, as I've been filling this here, and then producing the corresponding formula for this one. Although this one I'm not giving it to you as a handing exercise. Right. So what have we just seen? So I really went into detail here, but so it's an equivalence relation. So for any 2 points, in X, the curves from one point to the other. I don't know. It could be, the space could be really complicated, but all the curves from when I consider all the curves from one point to the other, and on the set of all such curves, I consider homotopy relative to endpoints. I get an equivalence relation for all these curves that from x0 to x1, and so I can partition them. So homotopy relative to endpoints partitions the set of all curves from one point to the other. Homotopy relative to endpoints is compatible with concatenation whenever concatenation is defined. Homotopy relative to endpoints is compatible with taking this sort of inverses, sigma minus. Up to homotopy relative to endpoints, concatenation is associative. The constant curves serve as neuters or as identities, as neutrons up to homotopy. And the sigma inverses, the sigma minus are inverses up to homotopy relative to endpoints. That's what this exercise says. And if you think about this, this means that this whole sequence of facts means that on the set of equivalence classes of curves, so given any 3 points, given any 3 points, x0, x1, and x2, concatenation descends to a well-defined operation on the sets of equivalence classes. And we actually have what is called a groupoid, because up to homotopy everything is invertible. So what we have is a groupoid, pi1 of x. So what is a groupoid in general? A groupoid is a category where every morphism is invertible, which is not the same as saying that every 2 objects are isomorphic. That is not the same. Simply because it could be that every morphism is invertible, but there could be 2 objects between which there is no morphism. But anyway, so a groupoid is a category where every morphism is invertible, or every morphism is an isomorphism. And then we form this groupoid by declaring the objects to be just the point in X, and given any 2 points, the morphisms according to this category, this groupoid, are the equivalence classes of the equivalence classes for the relation of homotopy relative to endpoints. So here I'm considering all curves from x0 to x1, but modulo homotopy relative to endpoints. And the composition in this category is given by, you see, if I have 2 curves, if I have 2 equivalence classes, and the curves in this equivalence class end precisely where the curves in this equivalence class begin. Then the composition is defined in terms of any representative. So I take any representative here, concatenate, and then take the corresponding equivalence class. But now, of course, the equivalence class from the beginning point to the end point. I mean, from the beginning point of any representative of this one to the end point of any representative of this one. And the point is that this is defined in terms of representatives, but is well defined, and actually the reason why it's well defined is this one. Okay, so we have a groupoid, and so you see somehow is a groupoid. So here what this does is a formal way of saying you start going from points in X to points in X, but up to homotopy relative to endpoints, and then it's kind of you just do it in an algebraically organized way, if you want. And the fundamental group of X based at any point. So I take here any point in X. So here X naught is in X. Is, and I denote by one of X comma X naught based at X naught, and it's simply the set of morphisms from X naught to X naught in this groupoid. Or in less fancy terminology, is the set of equivalence classes of loops based at X naught modulo homotopy relative to endpoints. I mean, equivalence class for the homotopy relative to endpoints. And it's a group under the operation defined in terms of concatenating representatives. And then a couple of examples, which are not hard. So fundamental group of Rn based at any point is the group with one element. Fundamental group of upper half plane based at any point in the upper half plane is again the group with exactly one element. And yeah, so this I leave you as an exercise. This is not hard. And then here our first theorem, what it does is it compares the fundamental group based at different points. So of course, so far I have not assumed that X is path connected. And so when it's not path connected, and we pick points in different path connected components, there is really no way of comparing the fundamental group based at one point and based at the other. But if I have a curve, then taking the fundamental group based at the start point of the curve, and taking the fundamental group based at the end point of the curve, they are isomorphic, and the isomorphism is given in terms of sigma, as you are seeing here. So schematically, what I have is here here sigma, and here is sigma of 0, sigma of 1, and and I want to go from this fundamental group based here to the fundamental group based here, and so I want to be able to obtain from some loop based at sigma naught some loop based at sigma 1, and then once you see that this picture, then you come up with what comes to your mind. So well, something I can do is just first go with sigma minus, and then take the loop that I was given, and then come back to sigma 1 by means of sigma. And that works, and it works as a group isomorphism. And then I leave the details to you. So this is our first theorem. So the first theorem, what it says is that let's say if you are in a path connected space X, then for any 2 points in X, the fundamental groups based at them are isomorphic, and each curve from one base point to the other gives an isomorphism. The isomorphism looks like a conjugation isomorphism, and the only unfortunate thing about this is that the dependence on the curve. So if you have a path connected space and you take two points in that path connected space, their fundamental groups, the fundamental group of the space based at those points are isomorphic, those two fundamental groups, but the isomorphism is not canonical. So somehow everything is nice except that the isomorphism depends on the curve. It's not completely canonical. Okay, and our next theorem says that, consider the following. So consider, let's say that I have my space X. I have my space X. I have a space Y. I have a continuous function. And then I decide to take the fundamental group of X based at some point. Let's say here is X naught, and then let's take the image of X naught under F. So Y naught, and then here just Y naught equal to F of X naught. And something I can do is every time I have a loop here, or every time I have a curve here, well, formally it's a function from sigma, from the interval 0, 1 to X, and something that I can do then it's follow sigma with F, and that turns out then to be a curve in Y, which if my curve was a loop based at X naught, then of course the following that with F is a loop based at Y naught. And if you think about it, every time I have some homotopy here, so every time I have a deformation here, which for loops looks like I just drew, that homotopy I can just follow it with F, and I still have something continuous, right? Because the homotopy goes from 0, 1 cross 0, 1 to X. So I of course can follow it with F, and then I would still have something continuous if F is continuous. And then what I obtain is just a homotopy here between the images of the curves under applying F. So what I'm saying is that if I'm given a continuous function, then I have then I have a well-defined map from the fundamental group based at X naught to the fundamental group based at the image at Y naught. Yeah, and well, this function is actually group homomorphism. But yeah, so but this says that it's well defined, but it's actually a group homomorphism. And it turns out that when I consider the category of pointed topological spaces, so definition, a pointed topological space is a pair consisting of a topological space and any point inside it. I have a functor from the category of pointed topological spaces to the category of groups that to each topological space, to each pointed topological space, associates the fundamental group of the space based at the base point considered in the pair, and each morphism of pointed topological spaces. So what is a morphism of pointed topological spaces? Well, it's a continuous function between the spaces that sends the base point to the base point. Right. So yeah. And then to each such morphism of pointed topological spaces, it associates this group homomorphism, and the theorem says that this constitutes a covariant functor from pointed topological spaces to groups. I'm going to leave it there, and in the next lecture we are going to relate these fundamental groups to certain type of covering functions. So let's leave it there.